Good morning again. Now, the last 3 days of the course will be here. Actually, today and tomorrow will be in that room, and the Friday there will be a CRC course, 1 day long. You will get the opportunity to attend to that course as well. And today's topic is still going on some basic science stuff. We already finished the cell biology in the first day, and some tissue engineering, mentality, and some experiences of Dr. Veden. And yesterday we had in biostatistics lectures for whole day, and today we are going to talk about some kind of biomechanics. Dr. Pahr, he's a biomedical engineer. If there's something missing, please correct me. And he's going to talk about the living tissues biomechanics. Of course, when we say some living tissues, in orthopedic surgeon's perspective, it means it's the bone and muscles and ligaments and etc. So he's going to give some informations about that. And then I'm going to talk about the clinical biomechanical applications, especially in the cases for the trauma and the fractures. And Dr. Huri also, she's a biomedical engineer. She's an associate professor as well. She's going to talk about the biomaterials. And then the program is going to be ended about the implant designs and the other stuff. So please, Professor, thank you very much for coming, first of all. Thank you very much.
Thank you very much. It's a pleasure for me to be here. A few words to my person. I'm originally an aerospace engineer. I'm associated to the Vienna University of Technology, and also associated to the Karl Landsteiner Private University, a newly founded university and medical school. And in this context, I'd like to show you maybe a slightly different view, a view from an engineer about bone and joint mechanics. This will be the topic of today. We will talk about basic biomechanics, some bone mechanics, and then also joint mechanics. Whenever you come to this topic of mechanics, actually this very nice saying from George Bernard Shaw always pops up. That means whenever you look closer to something, you detect you have even more problems and not less. And that's also when you come to the field of biomechanics. If you analyze the things, you detect, oh, there are much more things I have to detect, and what I'm telling you now is a very basic view of all this stuff. And let me start with engineering mechanics and the link to biomechanics. So this field of mechanics is actually quite old, and you see here Borelli in his work To Motu Animalum showed already here very simple, let's say, machines to lift maybe masses. And the interesting thing is, if you look at this, that's where the starting points of mechanics, where he analyzed more or less the state of rest of a body and the action of forces. And if you look at his sketch, there were already humans in here. That means, actually it was not the way that they invented new machines, but they was looking also even earlier, Leonardo da Vinci, they were looking really at the anatomy, and they're thinking, okay, what are the forces acting here to produce a motion? And that's actually mechanics. Mechanics is nothing else than you look at the statics or at the dynamics of a body, and our body is a biological system where you have bone, muscle, ligaments working together. Looking at this field of mechanics, it's actually a big picture, but why I'm showing this is to know, okay, if you're looking at engineering mechanics, you have to distinguish between solids and fluids. These are two different fields. We are mainly talking about this here today, and then you have to think about rigid bodies. It's a more or less nothing is rigid, but it's a simple approximation, and in reality you have deformable bodies. That means whenever you're looking at these two fields, You have to think, of course, also on statics, dynamics of a system, strength of a material, plasticity, and other things. And I only like to point out here the things in a very simple way. First, start with the type of motion. Motion means we can looking at, for example, linear motion along a line. We can looking about an angular motion if it's turning around an axis. And of course, what we know that usually we have general motions. That means we have a combination of a linear and a rotational motion, and that makes the thing quite difficult to describe what is the motion now of this jumper here. But these are the basic types of motion. That means a body under motion. That a body is really start moving, it needs a force. That means something needs to push the body, or we have here the concept of a momentum. What does it mean? Whenever you change the movement of a body, if I like to lift this, I'm applying a force. And forces are usually measured in newtons. And they usually have a direction and a magnitude. So the force, when I'm lifting this, the magnitude is really along the gravity. And there are many different forces. So you can have a spring force, a gravity force, you can have friction forces, all these kind of forces acting. And if you have a force, and this force is acting maybe here, you see on this device where you try to screw up a bolt, and you have a certain distance, then this force times the distance is the moment. So you say, okay, this bolt here feels a moment. And this moment is simply defined force times normal distance. And actually a force is producing a longitudinal movement, and the moment is producing a rotational movement. And if you have a combination of a force and the moment, then you get these general motions. That means these are the two ways, or the two, let's say, engines you need to produce a movement. So we're talking about movement and the reason, the cause of the movement. And now, usually we also have systems which are not moving at all. And this is also a concept we are doing, and this concept we call statics. That means usually, of course, if you're looking at civil engineering, if you're looking at buildings, nothing is moving. Actually, we assume it's not moving, or the movement is so small that we can say, okay, it's under rest. Then we talk about statics. And that simplifies the thing, because how can we analyze a law, or how can we analyze here a structure under static equilibrium? Well, there are three essential laws defined by Newton. And yes, dynamics, of course, is then if you have here a motion. These three laws from Newton are quite simple laws. Newton, you know, Newton was a very famous scientist, and there's also a story about Newton. At these times, Newton was also the editor of the one and only journal in England, and he was not such a nice guy than everyone means, so he was really controlling the publications, right? And there are people who say, okay, there were a few publications which were not going back to Newton, because someone was sending him a manuscript, and he said, okay, I had this idea already 1 year ago, so I'm publishing this under my name. But actually, these things are really from his side. So that's what, if you're reading up the things, and Newton had this power. And the first law of Newton is simple. If you're looking at all the forces acting on a system, and you detect that you don't have a net force, it means the sum of all forces is 0, then this system has to be in static equilibrium. For example, this table, it's not moving. So if you analyze all the forces which are acting on the leg, the forces from the gravity, they are in equilibrium. So simply speaking, if you have a table of 50 kilograms, every leg has 1/4 of this 50 kilograms. This is the force, and then all forces are 0. Now what does the second law say? Interestingly, you see there comes another term on the other side. It says the sum of all forces, or the net force, is mass times acceleration. What does this mean? The most simple thing is, if you're looking at gravity, if you let something fall, this is a mass, and what is the acceleration? The acceleration is simply the gravity, g. That means there is a force acting here, which is pulling the thing down. And depending on the force, on the mass, and on the acceleration you have, let's say here, an equilibrium. So that means if something is starting to moving, you have to have an acceleration. This is the second law of Newton. And then you're talking about dynamics. It means changing acceleration are producing forces. If you're moving, all the time the forces which are acting on our body are changing. And the third law of Newton are quite simple. It means actio reactio. If you have your hand on the wall, the force you feel in your hand is the same force which is in the wall. This is describing all kinds of motions. And if you're talking about motions, then there are two things you usually detect. Someone is talking about kinematic and kinetic. So how does this fit to this motion? Actually, kinematic is nothing else than to describe the motion. You see here this funny guy. I like this picture because, you know, they can play here and you see a very nice movement here. To describe this movement by a position, a velocity, or an acceleration, this is called kinematic. It's the pure description of the movement, kinematic. And now, if you add up to the kinematic the forces, then you come to the field of kinetic. It means to describe also the relationship between the forces and the motions, and of course the basics are the Newton laws. And then you're talking about you're analyzing the kinetic of a system. That means if you move, what kind of forces do you need? Because movement means only you move it, but the question is if you move it faster or slower, you have different forces. So that means we were talking about this, and we were talking about this, so know more or less also about this, and now we have here this naming a rigid body. So if you're coming to engineering mechanics, what are rigid bodies? And there is, I only picked out the most important concept of these rigid bodies, namely the law of a lever. What is the law of the lever? So if you have here a rigid bar, and you have here a hinge or a support, and you have a force here and a force here, then if we analyze the system, we first cut here this support to get the force in the support. It's an unknown force, and maybe we have also a moment here in this point here. And you see here this lever, we have many forces on it, and if this lever is not moving, it's in static equilibrium, then Newton law says all the forces on this lever have to be zero. In other words, all forces in the first direction, in this direction, have to be zero. This is fulfilled. There are no forces in this direction. If you're talking about the forces in the second direction, we have three forces. This force, and this force. So we have to write down these forces. And they have to be zero. This is Newton's law. And third, we have to say, okay, the moments have to be zero if it's in static. And usually, what's done in mechanics, you choose as a rotation points, you can choose any of these points, but the easiest thing is you choose the point of the unknown forces. Why? Because then if this is the center of rotation, you say this force times this normal distance plus this force times this normal distance has to be zero. And you see the unknown force is not in the system. But what we detect, first of all, from this equation, we could calculate the support force easily. But the most important thing is this one here, which says that you see here this force in the second direction times this distance has to be this force times this distance. And it's like you see it here. If we have twice the distance to the center of rotation, this force is only half. And if you have vice versa, only a shorter distance, this has to be bigger force to keep this lever in a static position. Now this sounds to be very theoretical, but actually this concept of levers are found everywhere in the body. So for example, looking here at the upper limb, you have here a support point, you have forces coming from the muscles, you have forces coming here maybe for lifting a weight. You have the same thing here in the foot, you have the same thing here in the head, and then of course we also see the example on the hip and on the knee. That means everywhere we have these levers. And why we have these levers, we will come to this in a few minutes. So that means analyzing the system, under rest gives you more or less the forces which are acting in the muscles or also in the joints. Now, what happens if we start looking at dynamic systems? Everything gets much more complex, and we saw that the sum of forces have to be mass and acceleration. And the same thing holds also for the moments. The sum of the moments have to be this J times alpha. What is this? This J is the so-called rotational inertia. That means that's the resistance of a body if you try to get this body into rotation. And you see here the inertia depends on the shape. Yeah? What kind of body you'd like to start turning. So if the inertia is quite high, the moment has to be quite high. If you assume here, and this alpha is an angular acceleration. So if you keep this constant, the higher this inertia is, the higher the moment has to be to produce this acceleration. And the same thing holds here for the force. Now the question is, well, what is this small g here? A quite an easy way to analyze a dynamic system like a human body is that you analyze the center of gravity. That means you see here this hurdler, and to describe here, for example, the forces which are needed to accelerate this hurdler over this thing here is simply the mass of the hurdler, the acceleration of his center of gravity, and then you can describe the forces which are necessary. And if you see here what happens, quite interestingly, that a hurdler always tries to keep the center of gravity more or less in a straight line. Why? Because if his center of gravity is going up and down, he would need to produce this up and down by muscle forces. So that's the reason why he tries to stretch his legs as good as he can and try to get the acceleration only in this direction, but not in this direction. Also, jumpers always try to have their center of gravity quite low if they have to jump over a rod or something like that. So that means this concept of the center of gravity is very important in mechanics to analyze systems. Dynamics. This is not statics anymore, it's dynamics. And now we are thinking, okay, we have a force, we have a movement, but we also need energy to do this. And this energy or also work in kind of very simple machines is defined by force times distance. That means if I have here, if I'm pulling this, I have a friction force. And if I'm pulling this from here to here, I have to put work into the system. And this work is the force, the pulling force times the distance I'm pulling. The longer I'm pulling, the more work I'm producing. And in case of this friction, what happens with this work? This work is simply lost. It's dissipated by friction. Now we have lots of simple machines, and a simple machine, as I defined this here, is something like a driving unit and a device. What is a driving unit? A driving unit in engineering is, for example, an electrical engine or a piston. So this is the force producing part, and the device is usually the force is not acting only in one direction. So you have devices, for example, like levers. That means you can lift a huge mass with a quite small force because of the law of the lever. Or you have, as machines, you have wheels. That means you're turning here with an engine, and depending here on this wheel, you get a rotation, and you can, if you place a ball here, it would fly away. Or a pulley. That means a way where you lift a force here, you pull on any kind of direction with a piston or whatever, and you lift here a mass. That means the function of the simple machines is, on the one hand side, to convert energy. You can convert energy from potential energy here, for example, to, if you have here a wheel, rotation energy. Yeah? You can also change the direction of forces. You can generate moments and all of these things. So this is the concept of a very simple machine. And why I'm talking about this? Because the simple machines are everywhere in our body. If you're looking here, for example, at our body, we only have one driving unit. And the driving unit are our muscles. So the muscles, you know, can only contract. So it's not like pistons, they can pull and push a piston. Yeah? So they can only pull. This is our only driving unit we have. And now this driving unit is acting with simple devices like with levers, with wheels, with pulleys. Yeah? Something like that here, to really make a very complex motion. But the basic systems are very simple devices. You always find this basic stuff here. Huh? You always find levers, we always find pulleys, which are used to do the locomotion. And that's now the link from mechanics to biomechanics. In principle, the message is the same thing. Only we are using biological systems. We don't have a piston, we have muscles. Yeah? We don't have a classical iron-made lever, but we have our bones, which are organized in a way that they also act as a lever. This was this field of rigid bodies. And now, what is the difference with respect to deformable bodies? Rigid bodies is quite a nice concept to analyze a system, to analyze the forces, the motions, but it does not answer the question, for example, when do the tissue rupture? So that means we need another concept. And another concept is deformable bodies. And deformable bodies means whenever we have some external loading on bones or on any kind of structure, we can have compression, tension, torsion, or bending. What happens, for example, if you're looking at the bending, but the same holds also for the other thing, we get a deformation. It's not, if you have a rod, I start bending a rod, it's not straight anymore, it starts getting bended. Sometimes you see it, but most of the times you don't see this bending. For example, if you're walking, you don't see that your femur is really bended because the movement is maybe 1.5 millimeters. It's near nothing. But it's still bended, and this bending produces, if you're looking into the material, for example, on this side, you are stretching the material. On this side here, you are compressing the material. That means you get something which is called an internal loading. You're getting stresses here under tension and stresses under compression. And what we know, if these stresses are beyond a certain limit the tissue is able to endure, then we will start fracturing or rupturing the tissue. So this is the concept of deformable bodies. And now, what do material engineers do? What they usually do, they plot, for example, in a very simple case of a rod under a force. You see, this is the initial length, and this is the deformed length. So you have an increase of length, and this deformation is caused by the force. And what they do, they don't analyze force versus this length change. They define so-called stresses, and stresses are the force divided by the area. Why? Because forces are not size independent. The bigger the structure is, the bigger the force. But if you divide the force by the area, and you double the area, you double the size of the structure, the stress is still the same, because the stress is Newton per square meter. And if you have a structure which is like that, and you double the size, of course and you'd like to have the same loading of the structure, you have also to double the force. But the stress is still the same. So that's the concept of this stress, and they plot the stress on this axis. And on another axis, they plot something which is called a strain. And the strain is nothing else than this length change divided by this initial length. And this is a dimensionless thing. And usually you can say, you can give this in percent. What does it mean? If I have a strain of 0.01, that means 1%. What does this mean? If I have an initial length of 100 centimeters, and I have a strain of 1%, that means the change of the rod is how much? It's 1 centimeter. It means a strain of 1% means you change the length by 1/100th. Yeah? It means usually we know that the rupture strain of bone tissue is around 1%. It means if you have a bone of 10 centimeters and you extend this bone, by 1/100, that means 100 millimeter. By 1 millimeter, you come into the rupture strain of the bone. So you see it's quite small. Yeah? So that means 1% of strain. And this concept is also quite simple if we want to understand it. And this is plotted here. And what we see, we have up to here a range where the stresses and the strains are linearly related. And this is the region here of elasticity. And we can describe this by a so-called material property, also E modulus. And the E modulus is nothing else than it describes how stiff is a material against tension. And for example, steel has an E modulus which is 210,000 megapascal. Bone has an E modulus which is only around 10,000. So steel 200,000, bone 10,000. For example, a polymer has only around 1,000 of E modulus. Yeah? Aluminum 70,000. So that means this is the quantity who describes how stiff is a material. And if I place an implant, steel implant into bone, I have to be aware that what I'm placing is 20 times stiffer than that what's in there. Because this is steel. And what is new? New is the so-called Poisson ratio. If you stretch a material, it always gets smaller. You don't see this quite a lot in bone, but if you look in tendons, you really see if you stretch the tendon, it's getting quite small. And this number here is characterizing the lateral contraction. So that means up to here, we have an E and a nu. But what's up to here? Here we're coming in a non-physiological range in case of a biomaterial, but in case of steel, we're coming to a plastic region. We will talk about this in more detail later on. What's also interesting, if you're looking at deformable bodies, usually we not only have the simple spring-like behavior, usually we have a spring and a temper. And the spring and the temper, you have it in a car. All the wheels are usually in such kind of a system. And this leads to some interesting behavior. On the one hand side, a so-called grip behavior. That means if you sit on the front of your car, you will detect that the car is still lowering up to a point and then it's stopping. This is grip. Or if you pull such a kind of a material and keep the distance constant, you will feel that the force is going down. This is relaxation. And the reason is this damping element. Because if you would have a damper with oil, the oil is simply coming out. And then you have also material behavior, which is, for example, hysteresis. That means you are loading something and you're unloading something and it's not on a line. It's having such kind of a behavior. Or you have a behavior, if you start loading a structure faster and faster, that you have a changing in this material behavior. So that means it's not so simple anymore. It's getting more and more complex. Why I'm talking about this here? Because my next session is about bone mechanics. And all this not so funny behavior actually is in bone. And let me first say a few words about bone and know that you know what it is, but still I'd like to repeat shortly. We have to be aware that bone is actually a material which starts at the atomistic scale, where we have collagen molecules and hydroxyapatite platelets. They are staggered here in a fancy way. These are the platelets, these are the molecules, where we get here the so-called fibrils. The fibrils are building bundles of fibers, and these bundles of fibers are building more or less something like a cross pattern, so layered structure, which are called the laminae, and these laminae are building the osteons. So the small osteons, which has a diameter of maybe 1/10 of a millimeter, they are built of such kind of a structure, and these osteons are building the osteonal bone. That means bone is a multi-hierarchical material. And the point is that the behavior at this scales might be affected on one of these scales. And what we know that, for example, calcification starts here and not here. That means if we have a problem here with calcification, or if we have a problem here that the collagen start getting problematic, then this behavior at this length scale has an effect on this here. What we are currently doing is that we are always investigating usually the things here may be here, but then we stop here. It's quite hard to investigate anything here. So, but you should be aware that we have also this tail here, which we have to take into account. And now coming to this bone head, if you test bone, looks quite similar to that. You have here an elastic region. You have a point where you get inelastic, and then you have here some kind of a plastic region where the bone starts to getting damaged. So usually physiologically you're anywhere here. What's important that if you overload bone up to a certain point, it fails. It breaks apart, like any kind of material. And up to this point, you see the area under the curve here is the stored energy. And what is energy? Energy is force times distance. That means the force times the distance. If you jump from anywhere, the force is the gravity, and then you have, of course, a distance. The energy is in your body, and it's simply released in your bone. And then this is equal to this curve here. So why is this important? If you're looking at bone, first, you have here a bone, and if you take your samples out of the bone under different directions, you would say, okay, it's behaving all the same way. So I'm taking the sample, I'm putting this in the material testing machine, I'm pulling on it. For the transversal behavior, I'm getting this curve. For this one, I'm getting this curve. For this one, I'm getting this curve. And if I have a sample which is oriented with the bone axis, I'm getting a behavior which is maybe twice or 3 times higher than the transversal behavior. What is the reason? The reason is the osteons. The osteons are aligned in the bone. And the osteons are made of these laminates. And the fibers, and fibers are always much more resistant in the longitudinal direction than in the transverse direction. It's like if you're looking at these new materials, carbon fiber reinforced plastics, in tennis racket, in skis, in all kinds of sport schools, but also in the implant system, you try to orient the fiber in the loading direction. And that's also what's done in the bone. Bone orients itself in the loading direction, and that means we have a so-called anisotropic behavior of the bone. So that means if we expect the behavior in this direction, it does not mean that we expect the same behavior in the transversal direction. This is, of course, if I'm putting an implant into the bone, actually depends the direction of the screw, in which direction is the screw in the bone, because this is influenced. And we see the variance is not 10%, the variance is huge. So this is something we have to bear in mind if we're talking about bone. But we also have to bear in mind, if you take a small piece of bone and we start loading it slowly, faster, 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 faster. What happened? This stress behavior is changing, and you see here the strain rate per second. So I'm applying a strain of 0.01, that means 1% per second. In other words, if I have a sample of 100 millimeters, I'm applying this 1 millimeters in 1 second. This would be this curve. If I'm applying the load much faster, I'm getting a different behavior. What does this mean? Bone behaving differently if I'm walking or jumping. The behavior changes. What is the reason behind it? The reason behind it is this damping. Because bone has something like damping activity, and the reason is that you see here also the effect, if you're looking at the area under the curve, if you have a trauma under low energy, you see usually a single crack or a few cracks. But if you have a high energy fracture, you have maybe a huge amount of energy in the bone which is released, and then you have a really severe destruction of the bone. So this is simply explained by this rate dependency of bone. But bone is also changing all the time, and bone is aging. That means if you look again at this behavior from the strain under the stress, you see that young bone is looking like this and aged bone like this. Interestingly, you don't see a change in the stiffness. So old bone is as stiff as young bone. You don't see a big change in the ultimate stress, but what you see is what? The area under the curve is quite different. That means stiffness and strength are the same, but the energy storage capacity is changing. And also trucks might lead to this effect, and then people say the bone gets glassy. Because glass is brittle, then that means glass is not able to store lots of energy. And it means when bone is changing, its behavior to this glassy type of material. The problem is that if you screw something in or if you do something with the bone, you have the feeling it's the same thing. But when you have an impact loading, it's fracturing much, much earlier. Or if you load it by a contraction of a muscle or whatever, then you have a fracture. The reason is because the behavior of bone is different. You don't see this difference. It's getting brittle. And only one more slide in this direction is whenever you're talking about bone strength, we're doing, of course, lots of lab tests, but in the last 20 years, more and more tests were done on the computer. And as an example, that's I'm working a lot in this field, so-called simulated bone strength. So if you're looking in the literature, this is a terminus which is quite often used. What does it mean? You have here this bone, and only as an example, if you're taking a full bone, but you can do the same thing for a biopsy. What you are doing is, if you simulate bone strength, you don't test it on a machine. You simply make here a CD image, quantitative CD or something like that, and then you do so-called in silico modeling. You model the bone, and you compress the bone on the computer, and you get here like fracture patterns to understand the behavior of the bone. What is the advantage compared to experiments? You can do this in vivo, and you can do this individualized. Also, you can do predictions. You could, for example, say, okay, what happens if I have a change here? For example, due to an implant or something like that, how does this change the behavior? And the simulated bone strength is getting more and more into this field. So this was now a basic introduction to biomechanics and the basic introduction to the behavior of bone. Because of the time limits, I could now start also doing the same thing for the tendons, for the muscles. But it would take some time because muscle tissue is behaving also in a different way. You have parallel things like bone, but you also have some distinct behaviors. But because the topic of this talk is bone and joint mechanics, I'd like to spend the remaining time talking a little bit about joint mechanics. And joint mechanics is quite an interesting field. Why? Because if you're looking, and I'd like to focus here on synovial joints, these synovial joints are usually classical joints. You have two types of, usually in the simplest case, you have two hard tissue types, usually bone. You have here an articular cartilage on these surfaces, which is smooth and slippery. And you have the joint capsule, and you have the joint cavity, which is filled by fluid. So a very typical, but also very special type of a joint in humans. So that means usually engineering joints are not looking in that way. They're looking differently. So that's quite an interesting way of joining two hard parts. And looking now at these synovial joints, how can they be characterized? So if you're looking at the different joint, at the different anatomical locations, you see we have pivot joints, we have hinge joints, saddle joints. So these are these pivot joints. We have these hinge joints here. We have saddle joints, and we have maybe ball joints. And the joints are always characterized by their kinematics. In other words, how many translations and how many rotations are allowed by the joint. Yeah? There are joints like here, for example, a ball joint. The ball joint usually don't let you move in any kind of direction because it's a ball, but it allows you a rotation in all directions. Yeah? That means you have maybe 2 or 3 directions where you can rotate, but nothing else. Then saddle joints, or let's say these plane joints, they have different characteristics. In other words, we can characterize them by the constraint forces, and of course, whenever we have a constraint, this constraint is producing a joint force. If I have here, for example, this type of hinge, we know, okay, we can have forces in all 3 directions, but we will not have moments. In this joint here, we know we can have forces here, but no force here. But we can have a moment because this hinge joint, like in the knee, of course, you can have here a moment, and the moment, of course, is then transferred to the 2 pedicles here. So that's a basic view to understand, okay, forces, moment in the joints, where do they come from? They come from the kinematics. And we have some basic movements of the joints. The joints can either roll. That means rolling means I'm simply having a behavior, you see it here, it's simply rolling. Or it can slide. Then it's not rolling, it's only sliding, or it can spin. And usually joints make all three of them. So you have a combination of a sliding, of a rolling, and maybe of a spinning. And based on the movements, we experience forces, but not only forces, we also have to talk about lubrications. And I only like to give it on one slide to say, okay, if you're looking into the movement here, you would actually also look quite about the lubrication of joints, the biotechnology. That means what we have here, if we have here these surfaces that the cartilage is touching, then we have more or less a so-called boundary lubrication. And if you're looking in this diagram, and we're looking at the friction coefficient, independence of the velocity of the movement, then we see if we have a very low velocity, then the two surfaces are touching, and we get here quite high friction. If we increase the velocity, and velocity means here really this sliding velocity, what happens, this inert fluid here starts coming into this cartilage, and this leads to a significant drop of the friction. And then we have here a hydrodynamic lubrication. There's a mixed lubrication, and then if we have it quite high, we have really a pure hydrodynamic lubrication. And that's actually what you'd like to have. Also in engines, you always try to get a hydrodynamic lubrication. That's the reason of the oil in the engine. The oil is pumped into all the bearings, then you have a small film of oil in the bearings, and this is reducing, on the one hand side, the friction, the force you need to turn something or to move something, and it's also reducing a lot the wear. And that's the big problem, the wear. That means that particles or whatever, that the surfaces are damaged and that you get problems here. And this is a so-called Stryker curve. You then see that you have to increase the velocity, and then the friction goes down. The problem is in the joints that you have changing velocities. You have from zero velocity to a very high velocity, but also you have changing forces. That means you always have a mixed type here. And if you have, for example, not enough fluid in the joint, then you automatically are on this side, and here you have a problem with wear. And if you have other damaged cartilage, for example, and you are at this stage, you know, then bone is more or less sliding on bone, and that, of course, is a big problem. So that means I will not talk more about this biotechnology. It's a huge field, but let's assume that everything is working fine in our joints. So, coming now to the next thing we have to look into if you're talking about joint mechanics. When you're talking about joint mechanics, we have to talk about axes. And there are several axes. On the one hand side, we have this anatomical axis. And usually they are defined locally, also if you're looking at the joints itself. For example, along the diaphyses, or you're looking at landmarks, typical landmarks, anatomical markers, where you can define this anatomical axis. Engineers like to have mechanical axis, and you see here, this is the anatomical axis, and a mechanical axis is an axis which is simply connecting the hinges. Because we know there are the forces, and we have to know, okay, what are the axes here for the forces. And then we have the so-called weight-bearing axis, it would be a connection from this to this. In the foot, it's quite a straight line. Depending, of course, if you have a varus or valgus deformity, then it's different. But that's what we need here are the mechanical axes, which is sometimes quite hard because we don't get this information. Because I see here EOS imaging, where you have a full leg imaging where you get this axis, right? But if you have only a small part of your joint, where are these axes? Mechanic axes. Anatomic axes are locally defined. And now, if we have this axis, I'd like to show you two examples to point out how a joint is feeling force and how it's working. So let's looking at the hip reaction force of a double leg stance. So we see here a person is standing, double leg stance, it's relaxed. We assume that we have a relaxed stand, so the abductor forces are more or less zero. And we're looking here at the hip situation. What do we have? Let's analyze the hip. We have here the two joint points. We have here the mechanic axis. We know that in this mechanic axis, here, there comes the force. So here's a force. And what we also know, if we're looking at the upper limb, we know, okay, we have also a force coming from the body. And here, it's 2/3 body weight. Why? We assume that we have 2/3 of the body weight up and 1/3 down. And if we stand like this and we're looking at the forces here, 1/3 is already below us and we don't have to consider this. And then it's quite simple. What we have is some kind of the system. We have 2/3 body weights here and the hip feels each around 1/3 of the body weight. It means if I have 100 kilograms, the force in the hip is 1/3, it's 30 kilograms. That's clear. And usually students, if you explain this, they understand this immediately, because this is basic mechanics. But if you now start looking at this situation, single leg stance. You'd say, okay, single leg stance, you're doing it the same way, right? That means we have now, of course, not 2/3 body weights, but we have also this 1/6 of this leg, right? So we have this 1/6 of this leg, and that's the load here. But the problem is, what we're doing, we are shifting the center of body weight. So this 5/6 is more or less the upper limb plus this one leg. And we have here this mechanic axis. The values here are millimeters, which are coming from anthropomorphic data. So roughly 70 millimeters, 36 millimeters. And now, if we cut the system, we have here a force coming from the joint, and we have here a force coming from the body. And the problem is, if we have these two forces and we're looking at basic mechanics, what is the problem? It would produce a moment. So, but this person is standing, so where is the other force? Well, the other force is coming from the abductor. That means this is the force now. Whenever you start changing your weight, immediately there comes a force here from this muscle. And now, how big is this force? Or in other words, how big is the joint force? We had here a joint force of 1/3 body weight. We have here a joint force of 1.5 body weights if you simply say, okay, this times this distance, this times this distance has to be in equilibrium. And if you say, okay, the force is the sum of this and this. And now what you get is that the force in the hip is roughly twice as high than for this situation. And now it makes usually you get this, what is really the loading of the joints? The loading of the joints is not the body weight. The loading of the joints are mainly influenced by the muscles. The muscles are the factor for the loading of a joint. And that's what is very simple experiment, or a very simple model. You see immediately on the one hand side, it's again a law of a lever. That's what you have here. And this force here is mainly dominated by this one here. That means the lever have to be in equilibrium. So this is from the hip side. I will also show you movies later on that you see, okay, if you change now, if you have a gate, then of course these forces are getting higher and higher. And now coming to the knee, if you're looking at the knee autonomy is of course, anatomy, sorry, is of course much more complex. I will not talk in detail. You know it already. The interesting thing is of course to have extension and flexion. You always need two muscles. That's clear because muscles can only pull, never push. And we have a few interesting parts in the knee. On the one side, the cruciate ligaments, and if you're looking at these ligaments, they are like crossings, and they are building something like a 4-bar linkage mechanism. So that means you have your 4 bars, and they are linked. Maybe if you're looking, bringing your car to a garage, maybe they have some similar device to lift the car. And what is the interesting thing here? If you now change the position of these bars, you see you only can have a certain movement of the joint, because these cruciate ligaments are constraining the movement. And of course, if you have weakened ligaments or ruptured ligaments, this whole movement is changing. It means the whole situation of the loading is changing in the joint. The second thing, which is quite interesting from the mechanical point of view, is the menisci. That means you have this lateral and medial menisci, and here then these crucial ligaments. But interestingly, what is the mechanical reason behind it? On the one hand side, this menisci is distributing the force. So if you would have a menisci and you are simply applying a compression load, you have quite a small contact area. A small contact area means a small area of the cartilage is highly loaded, you get damage and so on. If you have this menisci, you see it's distributed over a bigger area. That's one behavior. A second behavior, if you have a shock force, yeah, then this menisci, they act as hoops. That means you apply a compression. These compression forces are distributed to radial force in the menisci, and these radial forces are then transferred to so-called hoop stresses. And because the menisci is like a hoop here in the spiral, it's acting as a shock absorber. That means you cannot extend it in this direction. If you apply a force here, these hoops are constraining here the system. That means, of course, if you have a rupture, the problem is that this shock absorbing behavior is not there anymore. And that, of course, again, increases the loading of other parts and maybe damage of other parts. Now, coming also to a simple mechanical model of the knee, we have here in the knee these two bones. We have also here the patella, where we have here the patella tendon. That means analyzing the knee. What we have here is, if we cut the knee, we have two forces acting. We have the joint forces in the knee, but we have here the force coming from the patella. And if we have this case here, where this leg is on a stair and this leg is not on a stair, we have here the body weight. And if we analyze the system again, we see we have a lever. But the lever is more complex. And based on the law of the lever I showed you half an hour ago, you can analyze, okay, based on this anthropomorphic data we have here, the angles, we can simply analyze how big are the forces. I give you already the result here. So you have roughly one body weight in the knee, and we have 4 body weights in the patella tendon. That means this patella tendon here is the pulley. And this has extremely high forces. So if we have 100 kilograms, we have 400 kilograms here in the patella tendon. Yeah? And this is also an example, and of course you can do this, and I could now go over all different joints, and you can always do this very simple example to understand, okay, what's going on. Of course, what's clear here, the situation is changing during the movement, and that's what I'd like to show you here. For the hip, we are analyzing, you have the hip here, and you're usually analyzing one position. But now, what is, for example, the hip force if we have a movement? And what you see here, it's data from orthoload, where they use these instrumented implants. And what you see here are the hip forces, and also here the data, from this patient during a walk. And you can hardly read it. It says here 300 times 300. It means 3 times body weight. Yeah? That means, again, I'll let this run. In the hip, you see a force cycle. It's going up and down. You see here also in the hip that the force in the hip is changing. It's inside this so-called Bergmann cone. That means the force is not constant and it's always changing in the hip. And of course, what we do when we analyze the hip, we try to get out the most important and most critical force. So this is for the hip. Yeah? That means during a gait, we have roughly 3 till 4 times body weight in the hip. The hip bone feel around 400 kilograms, 3 till 400 kilograms. So that's quite a lot for an implant. And now, something which should not happen, but happened during this experiment, is you have a lady here, and she was stumbling. And she had this instrumented hip implant here, and what you have here, you see here 9 times body weight. So she had a short force peak in her implant of 9 times body weight. And that means, if you have a very old person with a very weak bone, this person did not really, there's no need to fall. If the bone is so fragile that she's simply stumbling, that maybe that's enough that she's breaking her bone, and then we have the so-called instantaneous fractures. They simply come from this biomechanics. Of course, usually that they're not very common, but still these instantaneous fractures are going back to this thing here, that you have 9 times your body weight on your femur. Only for a very short time, but that's enough that maybe a very, very weak bone is fracturing. Now, also thinking about if I cannot use an instrumented hip implant, but I'd like to know forces in the bone, what can I do? I can do something which is called motion capture. That means motion capture means you have a person with markers, you have a camera system, and you're recording the position of the markers in the space, and you can make here a simple model of this person. And here we see the pure kinematics, the movement of the person. And this movement of the person is step 1 for our analysis. Maybe you know these films here. So they're doing exactly the same thing. So usually they're doing motion capture to get the movements of the persons here. So you see here the actor, and you see here, and you know this was this avatar, and she's changing things. And of course they can then also change the size in these computer models. So that means this motion capture is not only in science, but it's also pushed a lot in movie industry. And what can be done with these results? We can do so-called musculoskeletal models. We can take these movements, we can model the skeleton, that means rigid bones, muscles, tendons, and can, for example, do analysis like letting the skeleton lifting a mass, and you see here, the bigger the muscles are, the higher is the force. You see also the forces here on the legs. And what you do here, you analyze this in a way you apply a movement, and you say, okay, what is the muscle force that you need the minimal energy? That means it's like the body is making a movement. So for example, if you have a gait, what you're saying, okay, how do all the muscles have to act that you have exactly this movement, but the minimal energy in the muscles? And then you get the forces in the muscles. Of course, it's a model, but it's working quite well. And for example, these models are also used for such kind of application. What do you think? What is this? You see here this, it looks a little bit strange for people who are not knowing this, so this person should be actually having a skin. For example, this is in automotive industry where they'd like to analyze what is the ideal position of a handle. If a person gets out of a car, so idealized position is they analyze in different handle positions and height of the car, and especially for elderly, they say, okay, if the muscle activity is as small as possible, then a person says, okay, it's quite comfortable to get out of this car. So that's also an application from these musculoskeletal models. Of course, you can also do in modeling many other things. You see here, for example, if you have an hip implant, what you can do, you can analyze the movement here, the kinematic data. You can make models where you can analyze, for example, force distribution. You can combine this as a wheel model to say, okay, what are the areas where I have lots of wear, and then maybe you can go into a loop and can change the design of the implant, improve the pressure, improve the wear, and so on. This can be done with a model without trying things out, but try to get the things on the computer first. And especially for the knee, here is also an example from a colleague from the United States, where he did a so-called open knee. So he modeled the whole knee here in a very fancy way, also the crucial ligaments, also the medial and lateral ligaments. And what you can do here, you can, for example, analyze the internal stresses. You can analyze the pressure. You can move this knee. Yeah? and so on. So only as an example that based on this kinematic data, you can then start doing modeling in silico medicine to get more information out of it. That's it. I hope you enjoyed it as I enjoyed it.
Thank you very much, Professor. It's really super nice presentation regarding the eye of the clinicians. I'm very impressed. Thank you very much. Please, questions. I'm sure you have lots of questions in your mind, you know, regarding the
Bir şey
biomechanics.
soracağım ama Ortopedi doktoru mu biyomekanikçi mi? Yani mühendis mi?
He's asking if you are a medical doctor or engineer.
I'm an engineer. So I studied mechanical engineering.
You can ask. We can discuss. We can discuss.
Sure.
Yes.
If I'm not able to answer the question, I simply pass it to the audience.
Yes,
Yeah.
Professor. I want to say something about your presentation.
Yeah.
Your pictures about hip reaction forces
Yeah.
are excellent, I think. They are thinking the main keys of the medialization action of hip arthroplasty, I think, and philosophy of the hip arthroplasty. Yes, these pictures are very important for the philosophy of the arthroplasty, I think, because I want to say something about this. You know it also, I think. Pelvic X-ray, teardrop signs, and correlation of these pictures and X-ray pictures are important, I think. Making hip arthroplasty, joint replacement surgeries. Maybe I can offer you with your future presentations. I think you made these excellent pictures correlation with X-rays. Maybe.
Sure. So I'd like to keep this as simple as possible and only give the idea in this very short presentation.
It's not simple. It's not simple pictures. It's I think excellent pictures because of explaining this these materials, hip reaction forces. These are good, I think.
Yeah. And I think also not only X-rays. So in future we also have to think about maybe also three-dimensional data. So that because X-rays are of course have more information, but usually maybe MRI and also especially MRI data, QCD data give you much more information. And what I also like to say here, this is only a static view here, right? It's a simple example. The real thing is this one here. That means, and this is changing in space, and this is changing for every patient because it's not only a small part that you analyze, because it's influenced by the whole musculoskeletal system. And if you never have a person which exactly the same sizes and the same muscle actions and so on, and the same gait, so that means what is our idea? Our idea is that we have, based on that, we validate something like that.
Weight bearing.
And that in future you have more or less on the one hand side as much data as you can. That means also having three-dimensional data, having maybe gait analysis, try to make behind such kind of a model. And the idea is that you select out of certain implants what would be the best implant you can use if you then finally also start doing such kind of analysis. Yeah? And maybe if you then say, okay, I don't have this implant, I need an individualized implant, that you're then really thinking about how can I make an individualized implant, especially for this patient, because there's no implant on the market which really is here in a good area.
Yes.
Mm-hmm.
Thanks.
Thank you.
For your excellent presentation.
Yes.
Hi. Thank you for a great presentation. I just wanted to ask a technical question. In the auto info, that where do you put the? I couldn't understand the markers.
In this very simple example, this is a suit where the markers are on.
Okay.
What you do, it's a suit, yeah. Then the next thing is, of course, would be from the mechanical point of view, the best thing is if we could use needles and place things pin on the bone. because you have here arrows from the skin. So if you place them on the skin, we know that the skin movement is quite a lot. There's one colleague in Australia, Marcus Bundy. What he did, he had a huge simulation thing with a moving X-ray. It's like 10 meters long, and what he's doing, he is really, when you move on this, he's making X-rays from the implant, and he's analyzing actually these things here dynamically to get rid of these skin movements. Yeah, but this is a huge effort. It costs millions, and it's a very complex system. So that means that that's one of the problems is exactly the accuracy of these measurements.
And the other one with the implants, the markers were in the implants, or?
In the implants, these were so-called instrumented implants. So what you have here, you have the implant, and inside the implant you have force transducers. And these force transducers, you can transfer the force here. You can hardly see it. There is a cable. It simply has a box here, but usually it don't need the box. The box is only there when they do the measurement. Otherwise, it's a classic implant, of course, a very expensive implant, even more expensive than that what you're using, because it's like a very special thing with a battery in it, and it's simply
you get the data from the implant.
Yeah, and you can do this not only for the hip. You see they did it for the spine. And actually, this is freely available, so that if you go to autoload.com, you see all these videos, these forces. They have the hip, they have the spine, they have the knee, they have the shoulder, and they have even sometimes more patients. So that means they have maybe here, for example, from the hip, they have walking, they have this steering, they have lifting a weight. So very interesting, and that's a unique data set which can be, of course, when you have no clue about the forces acting in a joint, this is a measurement. Yeah, this is really a measurement, of course limited to, in this case, only forces, but it's still a very, very good thing, and you see the dynamics. Yes?
Congratulations for a great, excellent presentation. My question is about stress fractures. Your engineer point of view on stress fractures, because we know that there are some overuse injuries with, for example, metatarsal fractures in runners, and they are overused. But we see some problems, for example, with skiing guys. They have really stiff ski boots, okay, and they have stress fractures from tibia. So it's not like tension or, I don't know, torsion or whatever, but just like the loading to the front cortex, okay? And I wanted to ask if you have any maybe information, maybe data on that way.
We don't have any data. So what you have, you come here to the field of also, I'm not sure if that's what you meant, also fatigue. That means that the material which is always loading, you see this if you have marathon runners, they sometimes have fractures, not because they have some trauma or something like that, because they're running too much. In other words, stone is always loaded, and it gets tired, it gets damaged. And these small micro cracks, usually we also have these micro cracks, but because we have also these times where we do nothing, where the remodeling process starts to repair these things. But if there is not enough time to repair it, you have a problem. So this is this side, but I think you meant something different.
Yeah, I think when you have like metatarsal fractures, there are ground reacting forces, and we understand it. But what way, just with squeezing, for example, bone or cortex, do we know if the remodeling goes that way, or there's no really force?
This kind of stress fractures, they are highly dynamic, and the material starts changing them, and this is a question of the rate, of the magnitude, of the way the force is applied on the bone. So we don't have any data. It's an interesting problem, but I cannot give you an answer on that. But it's coming in the material field, where you really see, okay, you have a problem. So analyzing this is, I'm sure, not very easy, because many factors are influencing this behavior.
Thank you for your excellent presentation. I just